Hi everyone, welcome. Today I'm going to talk about electromagnetic induction. I'm going to use the simulation done by Colorado University for you to understand the electromagnetic induction through the simulation. Okay. As you can see, there is a coil which is connected to a bulb, and also we have a magnet, and around the magnet we have indicated the magnetic field nicely. Very beautifully you are able to understand how the magnetic field lines are created around the magnetic field, these hypothetical magnetic field lines. So what do you call these magnetic field lines? You call them magnetic flux. And then the magnetic field lines are connected with the coil. Rather, magnetic flux is connected with the coil. We call it magnetic flux linkage. So what is the magnetic flux linkage? The magnetic field lines which are connected with the coil. At the moment, magnet is stationary. It's not moving. And also, you are able to see that there are some blue dots on the wires or on the coil. They are also stationary. Right. Now let's see what will happen when you move the magnet through the coil, towards the coil, away from the coil, and in various directions with various speeds. So you got to observe what are the changes which takes place when you move the magnet through the coil. Right? So you have to observe what happens to the bulb when you move the magnet. So I will allow you to observe yourself and then take down your observations. You can write down your observations. Then let's discuss once the observations are written down. Okay, let's start. Okay, what were our observations? We saw that bulb lights up when magnet moves. And when magnet is stationary, there was no current through the bulb. If magnet moves faster, intensity of the bulb increases. So these are our observations. What is required for the bulb to work? Electric current. Bulb needs electric current to work. What do we need to generate an electric current, cause an electric current? We need EMF. We need an EMF source. That is an essential. It's an essential part of a circuit. But when you look at this circuit, there is no EMF. Then what causes the current? Now this is the question which comes to our mind. Now we'll try to logically understand this situation. So as you can see, EMF source is essential in order for the bulb to work. In this scenario, what we observed was that when the magnet or the coil moves, there is a relative motion of magnetic flux linkage. So when the coil moves, the current is caused. That's what we saw. When the coil was stationary, there wasn't a current. That's why the bulb did not work. And as we know, the current can be caused by an EMF. So we can come to a conclusion: when there is a relative motion of flux linkage, we are able to create an EMF. So you got to understand this logical sequence. If I am to summarize, when the coil or the magnet moves, because of the relative motion of the flux linkage, an EMF is induced. So EMF can be induced by relative motion of magnetic flux linkage. The scientist Hans Christian Ørsted discovered that a current carrying conductor has the ability to create a magnetic field. Now when you think about this situation, the reverse of this situation, if the current carrying conductor has the ability to create a magnetic field, is there a way that we can cause a current using a magnetic field? That is where the scientist Michael Faraday discovered the electromagnetic induction. As you can see in the animation, when the magnet moves into the coil, a current is caused. So the Faraday found that the induced EMF is proportional to the rate of change of magnetic flux linkage. So Faraday found that induced EMF is proportional to the rate of change of flux linkage. So that means if the rate of change of flux linkage is higher, the induced EMF is higher. That's why we saw when you move the magnet faster, the induced EMF was higher, so that's why the intensity of the bulb was higher. When you move it slower, when you move the magnet slower, the rate of change of magnetic flux is low, therefore the induced EMF is low. Guys, now let's imagine that there is a beautiful girl. There's a beautiful girl and there's a boy who wants to start a relationship with the girl. So the boy wants to girl to become his friend. So the boy was initially rejected by the girl. The girl rejects the boy because the girl doesn't know the boy and she doesn't want any changes to happen, changes to take place. So initially she starting a kind of a friendship with somebody not known is not acceptable. It's not a good thing, right? So she rejects him. So then what happens is the boy also is also fed up. So he's tired and he think that he will stop trying to be her friend, and he goes away. He decides to go out. So when he's trying to move out, what happens is, then the girl wants him to not to go. Rather, she wants to just become his friend and maybe try to see what sort of a guy he is. So she tries to attract him. Now the force becomes opposite. So in both these cases, what you experienced was that there is a change going to happen. Right? The change was that the boy wants to become a friend of the girl, but the girl doesn't like it initially, because she didn't want to change herself. I mean, in her from the comfort zone she has, so she didn't want to change it. But then again, when the boy tries to go out, the girl feels like something that was in her environment now is going to change. So she quickly acts and she tries to attract him, right? So always she does the opposite thing, right? And why she does it? Because she doesn't want to change the current scenario, the current situation. She doesn't want to change the current situation, right? So this is very much applicable to us when it comes to our electromagnetic induction as well. So let's see how it is applicable to our electromagnetic induction. Pretty much applicable to our electromagnetic induction as well. Now when it comes to our electromagnetic induction, what we saw was when you try to move a magnet into a coil, so let's have a galvanometer here. So when you try to move a magnet into a coil, we could see that there was a reading in the galvanometer. So that means there is a current through the coil. The current through the coil can be only induced by EMF. So there must be an EMF. But in this circuit, it's a closed circuit, but still you don't see any EMF source. But when the magnet moves, the EMF is induced. How come that happens? So what happens is, when the magnet moves, the north pole moves into the coil will create a north pole based on the direction of the current. Right? So as we know in electromagnetic induction, the coil has the ability to create a magnetic field around the coil when there is a current in the coil. So the requirement here is that the coil needs to cause a current so that the current causes a magnetic field, and the magnetic field should be created in a way that the magnetic field of the coil rejects the power magnet which is coming towards the coil. That's how it should be created. So as a result, the direction of the current is being decided. So the opposite thing happens when the magnet tries to move away from the coil. Right? When the magnet tries to move away from the coil, what do you think will happen? The same thing like we saw in that example. Right? So what will happen is, the magnet is trying to move out, and what will happen is the coil will want to attract the magnet. To attract the magnet, the coil has to create a south pole. So then the magnet can be attracted. So in this case, the magnet is moving out. Right? In order to attract the magnet, coil creates a south pole. So accordingly, the direction of the current will be opposite to the previous direction. Right? Just to summarize, when the magnet is coming towards the coil, a north pole of the magnet is coming towards the coil, the coil creates a magnetic north to reject the north. Right? In order to create a magnetic field around the coil has to cause a current through it. How the current is caused in the coil? Through an EMF. Right? So automatically in this case, in order to oppose the change of the magnetic field, coil automatically induce an EMF within the coil. So the induced EMF causes a current flow. So the current flow is in the direction in order to oppose the change of the magnetic flux linkage, right? So that's how it is being arranged. You have the flux linkage this way. Right. Now let's say a south pole is coming into the magnet. If the south pole is coming into the magnet wants to reject the south pole. Then the magnet has to create a south pole. If the south pole is going away from the magnet, then the magnet has to create a north pole to attract the magnet. Always, the coil. So always coil is trying to oppose the change of the magnetic flux linkage it experiences. And accordingly, the current, electric current is caused by the induced EMF. So the EMF is induced so that it causes an electric current in a certain direction, so that the magnetic field is correctly adjusted in order to oppose the change of the magnetic flux linkage experienced by the coil. Right? So when there is a current, a magnetic field is created. But one important aspect here that we need to remember is the direction of the magnetic field. Direction of the magnetic field. The direction of the magnetic field should be correctly, rightly created. Right? So why it is important? Because the magnetic field of the coil has to oppose the change of the magnetic flux linkage created from outside. Right? So the direction of the magnetic field is important. Right? And also you need to understand that there's something important, that there is a change of magnetic flux. Change of magnetic flux experienced by the coil, right? And also the created magnetic field always in order to oppose the change, right? That is important, right? That is very important as well. Okay. It says that the direction of an induced EMF is such as to oppose the change creating it. Right? So the EMF is induced to oppose the change. Right? Now we can we'll try to understand this situation to understand the direction of the magnetic field created around the coil. So for that we can use electromagnet right hand rule. When you curl your four fingers to the direction, towards the direction of the current, your thumb of the right hand shows the direction of the north of the magnetic field created around the coil. Right? So this is what we saw. When the north pole is coming in, a north pole has to be created to oppose the motion of the north pole. The north pole is created in the coil. So the direction of the current then will be as per the diagram given here. If the north pole is going out, then the direction has to be opposite. So because the south pole has to be created as per the diagram that you can see. Putting Faraday's and Lenz's laws together gives an expression for calculating an induced EMF. Faraday's law told us that the EMF would be proportional to the rate of change of flux, linkage, and the minus sign of the equation comes from Lenz's law to indicate the opposing direction.